Hello friends, today we will discuss about the power electronics in continuation of the previous series of the DC to DC converter. Today we will discuss all the another types of converter like a boost converter. In the previous lecture we will discuss about the buck converter. These are the circuit diagram. Waveform we will already discuss, and the operation we will discuss equations, how the equation we are derived from the operation, and the application will be there. Now we will discuss about the boost switch mode power supply. The boost switching regulator is another type of switch mode power supply circuit. It has the same types of components as the previous buck converter, but this time in different positions. The boost converter is designed to increase a DC voltage from a lower voltage to a higher one. That is, it adds to or boosts the supply voltage, thereby increasing the available voltage at the output terminals without changing the polarity. In other words, we can say the boost switching regulator is a step-up regulator circuit. So, for example, a boost converter can convert, say, plus 5 volts to plus 12 volts. Means if the input is a plus 5 volts, then we can achieve a voltage of plus 12 volts from the same source. We saw previously that the butt switching regulator uses a series switching transistor within its basic design. The difference with the design of the boost switching regulator is that it was uses a parallel connected switching transistor to control the output voltage from the switch mode power supply. As the transistor switch is effectively connected in parallel with the output, the electrical energy only passes through the inductor to the load when the transistor is under the bias or off. This will be the circuit diagram. Over here we are finding that there is a slight variation when we are just compare it with the previous circuit. Over there is an inductor. In the previous butt converter, there is a switch, and again there is a diode. There is also a capacitor. The load will be a resistive load we are using over there, and the same kind of load popping over here. So once we are just compare or remember over the previous lecture, we are finding that the position of these three components will be different. This switch, it will be placed on this position. This inductor is placed on the position of the diode, and this diode we are connecting over this part, so it will be in the reverse direction. Just for that reason, while this switching device once is on, then the supply is moving straight forward, but one over here, and once this switch is off, then this inductor will be given the supply toward the load and with the help of the freewheeling diode. Now under the boost scheme, this diagram will be just to make some changes and the operation is entirely different. So over here, once we are looking that if the switch is on, the supply is moving from this to this switch and this. The path of the operation will be this one. So at this moment, the inductor will be charging with the help of this inductor, this switching device. But once this switch is turned off, the inductor plus the supply both will be added down, and it will be flowing through the diode and towards the load. Now the path is this, right? So this part will be disconnected from the circuit. So that is the difference. So whatever energy will be stored within the inductor, that will be added down with the source. So double, if we are saying that inductor is stored an energy which will be equal to the source, then twice of the voltage which will be delivered from this side towards the load, it will be given, right? So at that moment we can say that the double of voltage will be available at the source end, because one will be the Vi, another is the VL. So Vi plus VL is flowing towards the load side. So this is the operation of the boost converter. Now in The theoretical part, you can say about the waveform. First of all, we will discuss about through the waveform. Over here, we are the finding that there is an input voltage part of the on time and off time we are keeping as a constant. Then we are relieving over the voltage over the IV, the current which will be flowing over here. In this case, we are opting as a discontinuous system. Discontinuous system means whatever energy will be stored, whatever energy will be stored within the inductor, it never will be moving like this. So once the switch is off, at that moment, once the switch is on, the IV will be flowing over this. Once the switch is off, at that moment we are find that there is not much current will be flowing and it will be stopped at this moment. So we are finding that the IBM will be we are available over here, right? And the VG1 or the VCC, it will be continue this. Now output will be the same and the VCC it will be given the voltage at this moment, right? So this is the characteristics of the boost switch mode. In the boost converter circuit, when the transistor switch is fully on, electrical energy from the supply V in passes through the inductor and the transistor switch and back to the supply. As a result, none of it passes to the output as the saturated transistor switch effectively creates a short circuit to the output. This increases the current flowing through the inductor as it has a shorter inner path to travel back to the supply. Meanwhile, diode D1 becomes reverse biased as its anode is connected to ground via the transistor switch, with the voltage level on the output remaining fairly constant as the capacitor starts to discharge through the load. When the transistor is switched fully off, the input supply is now connected to the output via the series connected inductor and diode. As the inductor field decreases, the induced energy stored in the inductor is pushed to the output via Vin through the now forward biased diode. The result of all this is that the induced voltage across the inductor L1 reverses and adds to the voltage of the input supply, increasing the output voltage as it now becomes Vin plus VL. Current from the smoothing capacitor C1 which was used to supply the load when the transistor switch was closed is now returned to the capacitor by the input supply via the and diode. Then the current supplied to the capacitor is the diode current which will always be on or off as the diode is continually switched between forward and reverse status by the switching action of transistor. Then the smoothing capacitor must be sufficiently large enough to produce a smooth, steady output. As the induced voltage across the inductor L1 is negative, it adds to the source voltage being forcing the inductor current into the load. The boost converter steady state output voltage is given by this one. V output equal to V in upon 1 minus 1 minus duty cycle or V in upon 1 minus 1 D, 1 minus 1 minus D. As the previous buck converter, the output voltage from the boost converter depends upon the input voltage and duty cycle. Therefore, by controlling the duty cycle, output regulation is achieved. Note also that this equation is independent of the value of the inductor, the load current, and the output capacitor. We have seen about that the basic operation of a non-isolated switch mode power supply circuit can use either a buck converter or boost converter configuration depending upon whether we require a step down or buck or step up or boost output voltage. While buck converters may be the more common SMPS switching configuration, boost converters are commonly used in capacitive circuit applications such as battery chargers, photo classes, stop classes, etc. because the capacitor supplies all of the load current while the switch is closed. But we can also combine these two basic switching topologies into a single non-isolating switching regulator circuit called the unsurprisingly a buck boost converter. That converter we will discuss in the next lecture. Thank you for attending the lectures on the boost converter. Thank you.